Okay, gentlemen, we're going to take a look at points of intersection for rational functions. So you can see here in the notes, I'm on the bottom of page 8, right before the top of page 9. You had an example like this on the classwork the other day. For linear functions, we do the same thing, right? Which is setting them equal to each other and solving. Same exact procedure. Set them equal to each other and solve. Because we have fractions similar to when we're finding the x-intercepts, we're going to cross multiply and then solve. Okay? How many points of intersection can this should say rational functions, or actually no, leave it linear and quadratic, right? That would be a line and a quadratic. That was 2, or it could have had 1 or none, right? 2 quadratics could have none, 1 or 2, and we saw that last trimester. Similarly here, if we have a basic rational function crossing with another rational function, let's say I do it the other way, you could have, as we have here, 2 points of intersection. You could have them crossing about 4 times, right? If you have one of those rational functions that go like this, you could have it cross 3 times, right? It's generally for us going to be one that comes out twice, because if you got a cubic for it to cross 3 times, that would be a kind of a lengthy problem. So we're going to do this one, a similar example to the classwork. Find the point of intersection. So here's my 2 functions, because I want to find where they are equal, where the functions have the same x and y values. They would have to be set equal to each other. Cross multiplying x plus 3. Nothing's canceling like we have seen for x-intercepts, because there's a 0, but here there's not a 0. 2x minus 3, 2x plus 3. So I've set them equal to each other and cross multiplied. I'm going to FOIL to get the quadratics, right? I want to see how this all comes together, and then I want to set it equal to 0 to solve. So this is going to come out to x squared plus 12x plus 27. And this is going to come out to 4x squared minus 9. And so I FOILed, I got this. Similar to when we had points of intersection for quadratics and linear functions, you want to set this equal to 0. So you want to move everything around so that you have 0 on one side and all your other x's on the other side. I want to keep this positive, just like we had before, is I'm going to keep the x squared positive. So I want to move everything to the right-hand side. So I'm going to subtract x squared, subtract 12x, and subtract 27. Minus x squared, minus 12x, minus 27. So I have 0 equals 4x squared. Oh, sorry, 3x squared minus 12x. And this is going to be a minus 36 with a 9 and a 27. I'm looking at this. I have to factor now. Just like we have seen, whenever I have a quadratic, my first instinct is I have to solve for the x here, but there's x squared and an x, so let me factor. I'm going to take a GCF of a 3 out, so I'm getting a 4 and a 12. Divide by 3 on both sides, so that I make my factoring easier for myself, because I don't want to do with 3 times negative 36. 2 numbers that multiply to negative 12 and that add to negative 4. Negative 6 and 2. I finish my factoring. 6 and 2, or negative 6 and positive 2. So that means my x values, kind of like my roots of this, are 6 and negative 2. Those are my x values when every single time I've had to find a point of intersection question, I've had to plug the x values back in. So I'm going to draw a little arrow up here. 6 and negative 2. Okay, those are my 2x values, just like with linear quadratic, if you had two x values, you had to plug it in twice. Doesn't matter which one you plug it into. I'm going to just choose f. 6 plus 3, 2 times 6 plus 3. Getting 9 over 12 plus 3, that's 15. And that would simplify to divide by 3, 3 over 5. So that means one of my points of intersection, I write it over here, save myself some room, is 6 comma 3 over 5. That's one of them. That's an ordered pair. That is the point where my graph will cross with the other one. And then I'll use f again. You can plug into either one. I'm gonna plug into f, negative 2 plus 3, to negative 2 plus 3. So I'm plugging in negative 2 for my x's. There's my two x's I plugged in for. 1 over negative 4 plus 3 is negative 1. Comes out very easy. That is a negative 1. So negative 2, negative 1. These are my points of intersection. Similar procedure that we've seen before, set equal and solve. Because these are rational functions, you have to cross multiply, and then it's very similar to what we've seen before. Okay, that was the first part, so I have some more of that. Inverse, this was a little bit difficult. There's one little trick that I want to show you. For finding the inverse, same procedure again, swap the x and the y. Whenever I have a fraction and an equal sign, I'm going to cross multiply. X times y minus 4 is equal to 2y plus 1. That right-hand side just times this by 1, so that's good. Distribute my x, xy minus 4x. And I still have my 2y plus 1. Okay, I'm going to duplicate this over here so I have a little bit more room. Okay, now this is the important step, is you want to, our goal, if we remember, is solve for y. That's how we do inverses. Swap the x and y, solve for y. So I want all the y's together. Move the y's together. So here's an xy. I want my 2y on that side, so I'm going to subtract 2y. And then I want all the non-y stuff to the right-hand side, so I'm going to add 4x to that side. So now here's my y stuff, they're on the same side. And then my not y stuff is on the right-hand side. And this is usually where students get tripped up. So I want to solve for y, I want to get x. I want to get y isolated. But I can't combine these. I can't combine these at all. I would take out a GCF because they're both y's. So if I take out a GCF, I'm going to have a y, x minus 2. And now I have that singular y, 4x plus 1. In order to isolate that singular y, now I can divide by my x minus 2. So I get y equals 4x plus 1 over x minus 2. And remember, we write this as, if this is f of x, I'm writing this as f inverse of x. And there's my inverse. So you can see there's some similarities here, a negative 4, and then that's now an x minus 2 on the bottom. I have a 2x plus 1, I have a 4x plus 1 on top. So the numbers are all there. On your classwork, if you were to look at this one, which you started finding the inverse, this one, you would get this to come out. The inverse correct answer is actually the same thing. That is possible. It's just not common. So this is its own inverse. Not all the time will that occur, but just by the kind of the choice of the numbers, I have an x and a 1, a 6 and a 3, it just happened to work out that your inverse here is the same. Okay, if we were to just take one last look, what's my domain here? My domain would be all real numbers except -4. And my domain here would be all real numbers except -2. If you remember from the last trimester, your domain and your range flip when you're finding the inverse because you're switching the x and y. So this domain of the inverse is my range of the original. And this domain of the original is my range of the inverse. So a cool fact, that's why we had stopped doing range in most of our notes, because it's a little difficult to find, and this is a nice way to find it. It's a little difficult if these become squared and the rational functions become a little bit more difficult. But for somewhat basic functions, the domain and the range is easy to find for inverses, and then that'll tell you the domain and range of the other. Okay, so those are the two last problems you had to do. You have a couple of these, and I want to do one more stuff in the beginning that I did not have you do. Briefly, when we had functions that went like this, and we did this on the whiteboards, that meant that your function slid up by 2. So instead of being like that, it was like that, up by 2. So when I have my +2 on the outside, that slides it up. If it were -2, it would slide it down. If I had my rational function and there was a -2 over here, that meant that your domain skipped the value 2, and we drew this on the whiteboards. That meant that here's my 2, my graph slid over. So even though it said -2, I really went to the right by 2 units. So when it was underneath the radical change, it changed my domain, which moved it to the right, right? The negative moved it to the right because my domain skips the number 2, and that goes to the right. When the number was on the outside, that slid my graph up or down. So this is just a very fancy way of saying the same thing. We're giving a function that has a vertical asymptote at 4. Here's 4. And a horizontal asymptote at -1. So here's my -1. So it looks like I probably do something like that and like that. Here's my 4. Here's my -1. So that's my starting position. If my graph is slid over and translated, where would be the new horizontal asymptote? So this +2 is telling me that my graph is going to go up by 2 units, meaning my horizontal asymptote would not be at -1 anymore, would be at y = 1. Because if my horizontal asymptote is at -1, I slide up by 2, now it's at +1. If this -3 is telling me I'm going to move to the right by 3, just like it did up here, right? It switches my domain, it moves it to the right by 3. My vertical asymptote is going to be at x = 4, slid over to the right, now it's going to be at 7. So the key with these is understanding that the plus and minus on the outside is moving my graph up or down, plus up, down minus. But the plus or minus on the inside, plus inside moves it to the left, and minus inside moves it to the right. And that's based on the domain. Right? If I set that equal to 0, I'd get a 3. So I'm moving to the right. That's a positive number. If I set this equal to 0, I'm getting a -3. So I'm moving it to the left. Okay, so I'll do the last one, number 4. Actually, I'll do number 3. This would slide it down. Actually, I'll do number 2, sorry. This will slide it down. So my horizontal asymptote, starting at -1, would slide down by 2, and now would be at -3. My vertical asymptote, which is currently at 4, if I'm doing the second problem, +3 is going to move it to the left by 3. So now it's going to be at x = 1. And so just understanding that the inside is related to my vertical asymptote, where the signs are opposite. and the outside is relating to my horizontal asymptote, and that is just sliding up or down. Okay, so I'm going to give you some problems. You're going to have basically the first 4 to work on. I did 2 of these for you, but they're similar to the first 4 of these, and you'll get some inverse and some inverse and points of intersection. Okay, good luck.